Okay. Hello, everyone. So, this is the third week of the interaction session on this course on robotics basic and selected advanced concepts, right? This course is by Professor Ashitava Ghoshal from ISC Bangalore. So, my name is Soumya, and I have been your TA and will be continuing for the next 8 to 9 weeks. And then, yeah, just a reintroduction about myself. I am a PhD student at IIT Gandhinagar, and I'm your TA for this course. So, last time we did some questions. So, what we had done last time was basically TH parameters. I hope everyone had attended. So, it was initial lecture was a very basic lecture, and the last time we did questions on DH parameters. We learnt about what are the elements of robots and if their joints and links, and then how do we uh, write the DH parameters, and why do we even use DH parameters if we have already we can multiply the rotation matrices and find out the transformation homogeneous transformation matrix. But why do we even go for DH convention? And we came to know that yes, it is a very standard way of doing things, and our parameters reduced to 4 if we fix certain rules, and or if we fix some way of doing it. We have a certain convention that we follow. For example, the z axis has to always lie about the lie along the axis of rotation and along the axis of the prismatic joint also. That means along the axis of translation, right? So we have already seen this, and we wrote DH parameters for a few robots. We also saw what is the general form. I had referred to a video as well. I hope you have watched our video. So we get a very compact form, a compact matrix form when we use the DH convention. And once we have that, we can just directly plug the values into it in terms of the thetas, phi's, or whatever, and then we get the answers directly. So this matrix has to be just put in MATLAB, and you put in the values, you get the transformation matrices, right? So for each transformation, be it from first link to second link, and the number of links that you have. All right. So I think this was completely clear. I hope this time you have gone through the lecture. Did you get a chance to go through them for the week 3, which is kinematics of serial robots?
Yeah, quite well done though. I think the inverse kinematics was quite more involved and very interesting.
Okay. Anyone else? So, if you remember in the first class, I had asked a question: what is the difference between direct and inverse kinematics? And uh, it is one of the very basics that we cover in robotics, and we should know what is happening. Why do we have problems when we are solving inverse kinematics problems? Why direct kinematics is very straightforward and we get just unique solution, but for inverse kinematics we can have multiple solutions, and there is not a particular way to solve it. There can be multiple ways how you try to eliminate the variables and come to a particular conclusion for all the joint variables. Okay, so in this lecture, so it is highly advisable, because I won't be able to cover all those 4 hours completely into this lecture, provided I have to solve some questions for you, because then it would be easier for you to solve the assignment. So it is expected that you go through all the lectures beforehand. Okay, because I'm taking the sorry.
I have a question.
Yeah.
We know that in case of hook joint, there is a 2 degree of freedom.
Mm-hmm.
But when two links are connected by a hook joint, the degree of freedom in the system is 8. How it It's possible. Please explain.
Okay. So I think I'll have to get a figure. Uh, just a second. So we can take that question at the end of the lecture, if that is okay for you.
Okay, ma'am.
Yeah, then I'll switch my screen to laptop and then I'll be able to share the screen. So as of now, it is connected to my tab and it is on record. Okay. So okay, so before starting the questions, I'd like to revise some of the concepts so that you can recall the things properly. And then after that, we'll solve some questions. And then, Manas, I'll take your question. Okay. So let's start with very basics, like what is a serial robot? Like you might have already seen from the contents of the lecture completely that there are serial manipulators and there are parallel manipulators. So how is the serial, because next in the next lecture we are going to focus on parallel manipulators, right? We are going to see how do we write the kinematics for parallel manipulators, but before that, serial should be very clear to you so that you get a good understanding there. So what is a serial manipulator? So it is basically a mechanical system, right? And it consists of rigid links connected in series by joints. Okay. And what would happen? What would be the other property? That one end is fixed to the base and the other end is carrying a tool, or it is an end effector. Okay, so basically, what happens if we talk about a 3R manipulator? Let's say this is the fixed base of the robot, then it would be like this. Let's say this angle is, sorry, this angle is theta 1, this angle is theta 2, and let's say this angle is theta 3. So it has an end effector here. Let's say till here. It has an end effector here. This is your end effector. It can be a tool or it can be uh, it can just be an end effector which is supposed to manipulate the environment. So each joint here allows relative motion between links, and motion does propagate from base to the end effector by tweaking the joint variables. Examples are robotic arms. So if you have gone through the lecture, you might have seen that there are 3R planar robots. There is Puma, there is Scara robot, right? It has, so what does it have? It has RRR, and then there are 3 wrist joints. 3R has all RRR and Scara has RRP. R means revolute joint and P means prismatic joint, right? Prismatic joint means you'll be able to translate only, and revolute joint means you'll be able to you'll be able to rotate around that axis along which the joint is there. Okay, so in kinematics we study motion only. This is the first thing that we need to be clear. Okay, we do not study forces or torques here. If we talk about forces and torques, all of this come into dynamics. Okay, but as of now we are just doing the kinematics of the robot. Okay, so no, if there are no dynamics, that means we won't have any mass, we won't have any inertia, any friction, any force coming in. It would just be geometry of motion. That's it. Okay. Okay. So since now we already know what are serial robots, so if I want to define degree of freedom, how I would define it? Like, what is a degree of freedom of a robot? I think we had some discussion in the last class, but still I want to discuss it because now we can have the formula and we can know that how we in general define the degree of freedom. But I want to know the definition.
It's about how many motions are allowed. For a trainer, you can have at max three motions. For 3D spatial, you will have six motions. And
Exactly.
some of them will be constrained because of how you define the joints, revolute or prismatic.
Right. So you're perfectly correct. For a planar robot, we can move only in three directions. If it's, for example, if this robot is a planar robot, it is not if it cannot move out of the plane, then we can only have x, y, and theta for each of the links. But if we do not have a planar robot, let's say it is able to move in all 6 degrees of freedom, that means it can move in x, y, and z direction. It can also roll, pitch, and yaw, right? So we can write phi, theta, and psi. So if all of this is possible in general, then it would be 6 degrees of freedom. For planar, it is 3 degree of freedom. In general, for any robot, if you are supposed to define, for example, we had taken an example, if there are, this was covered in the lecture as well, right? If there are two balls, they independently have 6 degrees of freedom. This has 6 degree of freedom, this has 6 degrees of freedom. But as soon as you connect both of them, the total degree of freedom becomes 6 plus 1. Why? Because both of them have become one body. So because of it, it can only it can only move and translate along xyz and rotate along the along these axes, right? Apart from that, it can just move. So this is a revolute joint. It is, if it is hinged here also, we won't even have that, but it is a revolute joint, so it can have a degree of freedom to rotate about this, right? So because of those reasons, we had 12 degrees of freedom, but then 5 of them disappeared due to constraints, and we are left with only 7 degrees of freedom. All right. So in general, if we have to define what is a degree of freedom, it is number of independent parameters required to describe the configuration of a robot. So if you've gone to the lecture, you might have seen a formula for degree of freedom, which is lambda n minus j minus 1 plus sigma fi, where I is from 1 to j, right? So what did these terms mean? N was total number of links that we have in the robot, including the base. Okay. J is J is number of joints. Fi is degree of freedom of the ith joint, and lambda is like 3 for planar systems and 6 for spatial systems. Right. So this is how we define what is like, how do we find out the degree of freedom. For example, in Puma robot, what happens? Rn is 7 because we have, why 7? Because we have 6 moving links and one base. So it is 7. uh, J is number of joints, which is 6, right? Each joint is revolute. That means Fi is equal to what in that case? Fi is degree of freedom of ith joint. For a revolute joint, what is Fi?
1.
Right. Good. It is 1. And since it is a special robot, lambda is equal to 6. So my degree of freedom is 6 because it is lambda into n minus j. That means 7 minus 6 minus 1, right? Plus 6 because of this FIs. Sorry. 6 because of this, yeah, summation of FIs, 1 each. So it in total it is 6. So Puma 560 is a 6th manipulator. Now you can understand like this also. If you don't go through this systematic procedure, you can say that it is a spatial robot and it can manipulate anything in the environment in XYZ and orient in any direction. So it has 6 degrees of freedom. Whereas this is what you get from the formula as well. Right? And what is this called? Kepler Kutschbach criterion. Right. So there are a few misconceptions that I want to clear. One of them is that degree of freedom does not mean number of links. Not at all. Degree of freedom, but does mean number of independent actuators. Okay. So let's say you have a 3R robot and then you want to say that I want to place two motors over here at this joint. Both of them cannot act independently, right? But the motion of one will definitely affect the motion of the other motor if you place it anywhere there at that joint. So if you have multiple motors, let's say you place 4 motors for this planar robot, then also your degree of freedom is going to stay 3 and it is not going to stay 4 because 2 motors here are dependent. All right. Okay. So I think if we now understand how do we go from this formula to arrive at degrees of freedom, sometimes intuition also helps you to answer the questions. Okay. The next thing is, what do you understand by joint space and task space? These are the terms which we'll be using often. No idea. Okay. So there is something called joint space and then there is something called task space. We don't stick to one always, we keep on changing based on our requirements. Okay. So what happens in joint space? We have variables describing joints. Okay. Variables describing joints. It can be revolute, it can be prismatic, as you already know. Revolute can be denoted by, let's say, theta I and prismatic by di. Okay, so basically q theta 1, theta 2, etc. to theta n ka transpose is my joint space. All right. So if you're working in joint space, you're basically describing the joints, how it is oriented. You're dealing with joint variables. What happens in task space? It is variables describing end effector pose. Okay. So for planar robot, let's say, We are concerned about end effector. Then what do? We define x, y, and theta, which naturally says lambda is 3. And for spatial robot, we have x, y, z, and so before this, I was writing these terms, right? Phi, theta, and psi always. Is there any other way with which I can, just by adding one thing here, I can define that, okay, it is a function of phi, theta, psi? Obviously, the lambda here will be 6. But what could be that one thing? Any guesses?
Rotation matrix,
Yes, correct.
orientation.
Correct. So we can have just rotation matrix. If you write rotation matrix here, that means it would incorporate all the values of phi, theta, and psi. So this is a compact notation. Okay. So in kinematics, which we are doing and which we'll be doing in the next class as well for parallel manipulators, we would basically be mapping between joint space and task space. That is our complete goal. Okay, we are not including any forces, but we are trying to find out how does the joint variable link to end effector position. Now it can be directly done. You have the joint variables and then you want to find out where is the end effector position. It is direct kinematics. If you have end effector position and then you want to know what are the joint variables, is called inverse kinematics, right? So these are the two fundamental problems in kinematics. So one is direct kinematics. So what do we do here? Given joint variables and robot geometry, find the position and orientation of the end effector. Okay, so mathematically what we can write? Uh, we want to know where the nth link is positioned or oriented, how it is transformed with respect to the base, which is 0. It is a function of theta 1, theta 2, and so on till theta n. All right, this direct kinematics is always solvable. You do not encounter any problem. It has a unique solution, because if you fix the values of theta, definitely you are going to attain. So if you fix the values of theta for this robot, theta 1, theta 2, theta 3, there would be a certain end effector position which you will be able to obtain, provided you have theta in the correct ranges. Now if you do something such that these theta so there is something called workspace, right, apart from what we are reading. So workspace is the place where the robot's end effector can reach. Like it cannot go in any arbitrary position and anywhere. For example, if there is a 2R robot, this L1 and L2 link matters, and you cannot bring the robot in this range if you have joint angle limits here. Like if you do not have and it can collapse, it would be able to come here. But if you have joint angle limits, which we usually have, you won't be able to cover this. So we'll have a question in workspace as well. But the thing is you'll always have a unique solution provided you decide the joint variables, right? Your end effector position will always be defined. This does not happen in the case of inverse kinematics, and I'll come to that in a while. And so, and what happens? It uses matrix multiplication only. Okay. Whereas what happens in case of inverse kinematics? uh, given end effector pose, find the joint variables. Okay, so basically I want to find out theta 1, theta 2 and theta n for any given transformation matrix. That means I have been given that, okay, this is my end effector position, and let's say my end effector wants to track a position which is somewhat like this. Okay, so if this is the path I'm supposed to track, what should be the joint variables? So if I want to find the inverse, it is called inverse kinematics, and it is a bit difficult to solve. And why is it difficult to solve? Because it may have no solution, it may have multiple solutions, and it may also have infinite solution. So can you tell me, if let's say I have a 2R manipulator, okay? So that means I have two links. This is a revolute joint and this is also revolute joint, all right? If both of these are revolute joint, and let's say I want to reach this configuration, this place. This is my x, y and theta coordinate, that I, theta 1 and theta 2 both. This is my the position and orientation of the robot, or this is the point in the plane where I want to reach. Okay, if I want to reach it, how many ways it is possible that I would reach this point? Like, assume it is in the workspace and my robot would be able to reach that point. The values of theta 1, theta 2, L1, L2 are sufficient for me to reach there.
I believe it will be
Sorry.
two ways you can reach the point, elbow up and elbow down.
Right, right. So you can either reach in this configuration or you can reach in this configuration. So these are called elbow up and elbow down configuration, and both of these are possible if you have just these conditions set defined, and then you want to find out what are the joint variables. You might not have a unique solution, you have two solutions in this case, but think of it as a planar robot and you're able to understand this easily. But if it happens in space and if it is a combination of many links, we don't know how many solutions are possible. Like, it can be many ways in which the same thing can be achieved. So doing inverse kinematics is a bit difficult. Okay, sometimes we also need to solve optimization problem. If you have gone through a lecture, you might know that we need to optimize to find out what are the angles that I should choose given the constraints. What are the best minimum possible minimum thetas that I move to, that I need to move to, right? So we solve in that way as well. Okay, so uh, for direct kinematics, general formulation. So if you use DH convention, it is, I want to reach to uh, nth joint with respect to the first joint. So it is the multiplication of the transformation matrices, right? Depending on how many links we have. Okay, so each matrix is a 4 cross 4 homogeneous transformation. And why do we say 4 cross 4? Because the matrix for transformation looks like a rotation matrix, a translation term, translation vector essentially, and then the zeros over here, and then 1. Right? You might have also, so this has 3 cross 3 element, this has 3 cross 1 element, this has 1 cross 3 element, and this is 1 cross 1 element. So in total it is 4 cross 4. All right. So important practical advantage that we have in this direct kinematics problem is that once it is computed, the nth joint position or end effector position with respect to the base does not change if base location changes. Right, we do not have any problem if we change the base location, because it is basically transformation between both of them and it does not depend on where is the initial position. You can always define the origin at the base. If you have even taken some other coordinate system, you can always define it. It is in the robot's frame or tool geometry changes. Any of these changes take place, it does not matter, because what we care is about the transformation between the base and the end effector, right? So if we talk about planar 3R manipulator, so what does it have? It has 3 revolute joints. The link lengths, let's say, are L1, L2, and L3, and the joint angles are theta 1, theta 2, and theta 3. Sorry. Okay, so if you remember, what do we get here? Let's say this is my first link, this is my second link, and this is my third link. So the angle that makes it the base is theta 1. The angle with link 1 is theta 2. This is very important. All the angles that you are writing, the first one is with the horizontal axis, but the other angles that we are looking at are not with the horizontal axis, and it is with respect to the previous link. Okay. So once you write this, you can write, so let's say we want to find out the coordinate here, x, y, and let's say phi as well. Phi is for angle. So if I want to find out x1, what it would be? So this is L1, this is L2, and this is L3. So we want to, in this case, we want to find out what is the horizontal component, because we are talking about x, right? So x would be L1 cos theta 1 plus, what would the term be with L2?
Yeah, cos of theta 1 and theta 2 together.
Right. So since that is why I said that we are having this angle with respect to the previous link and not with respect to the horizontal. So this is basically theta 1. So here we'll have theta 1 plus theta 2. Similarly, for the third link, we'll have L3 cos theta 1 plus theta 2 plus theta 3. Right. Similarly, if we talk about y, it is just in the vertical direction. So it's just going to have sine terms. So L1 sine theta 1 plus L2 sine theta 1 plus theta 2 plus L3 uh, sine theta 1 plus theta 2 plus theta 3. And about the orientation that we'll have at the end would basically be a combination of the 3 thetas, right? So what do we observe here when we write this? This is very important. This you can always do. It is even more simplified for 2R robot. You do not have theta 3 come and theta 3 and L3 come term coming in. That's it. Okay, so if we can explain physically what happens in x and y case, each term that we saw right now adds one more links contribution, right? And orientation is just the sum of joint angles. Okay, so let's do an example. Well, it won't be very conceptual, it would be just doing it for this robot. So let's say your L1 is equal to L2 is equal to L3 is equal to 1, or L1 and L2 are 1, and L3 is 0.5. I'm doing this because you should practice it, because you might have similar questions coming up in assignments or exams. It is very standard robot, and you should get very clear with how we are like defining x, y, and phi. If it is even more difficult, like if it is standard 6R manipulator or 6 DOF manipulator, sorry, if it is there, then you have to do a lot more work. You have to write DH convention, etc. So what we studied in the last class would come as help to you. So theta 2 is 45 degree and theta 3 is 15 degree. Can you calculate and tell me what is x, what is y? And phi is very easy. It is just combination of these three angles, theta 1 plus theta 2 plus theta z. But can you tell me what are x and y positions? It's just to get a hang of what we derived. And I'm not going back to that page. You cannot write it down by looking at it. You draw the figure, you tell me what is x and y, and then you please answer these both for me. X is equal to 1.12. Okay, that's correct. So in the third place, I think you can have 2. And what is y? $2.46. No, that's not correct, I think. Check your calculation once again. Yeah, 1.96 is correct. Good. Okay. Can you do the same for SCARA robot? So SCARA robot is RRP, right? Just a second. So before that, when we concluded this, we can say that given the joint angles, we can uniquely get end effector positions, right? If we talk about SCARA robot, So it has two revolute joints and then it has one prismatic joint. So based on that, can you tell me what is x, y, z? So you'll have z also coming in there if you can understand. There are two revolute joints and then so it is uh, like motion mainly in horizontal plane but orientation only about the z axis. So position is given by xyz and orientation is given by phi, right? Phi is just combination of theta 1, so it has I think I should pull up a figure. I don't find it out right now with me. Just a second. If you can look into the slides there also you'll get, but okay. So not getting a good figure for it. Okay, I think this should be good. So let's say this is your base. Okay, your base is fixed and then this has a revolute joint here. So this is the axis about which the revolute joint is mounted. It is like this. Okay, so let's say it is rotating by an angle of theta 1 and this is your base. So here you will define z naught and sorry, not x naught and y naught. You know very well for dh parameter, like right, like z naught is always along the axis and then x naught can be taken in any arbitrary direction for the base and y naught is just x cross y is equal to z, so it should satisfy the right hand thumb rule. Okay, so this is the revolute joint and we have theta 1. Then there is another revolute joint which has this axis of rotation and it is theta 2. Okay, and here we have another so we have a prismatic joint attached here. So it is basically, so this is the axis along which it moves, right? And this axis has a tool at the end. All right, so it can move forward and backward by L naught. Okay, we can also call it to be D3. You can answer in that term. And then we are just interested in finding out what would be X, Y, and Z for this. And let's say this link is L1, this link is L2. What would you get for SCARA robot? There would be a Z term coming in, and the reason why Z term comes in is you can move out of the plane because you have revolute joints here, and you can definitely move out of the plane using this revolute joint. Then you can use this for linear operations. So this is a prismatic joint. So how far do you move? How you can relate it with it?
So in this picture, X and Y are in plane and Z is coming out of the plane. Is that correct?
Uh, for fixed base, Z is always along the axis of rotation
Correct.
or axis
Correct.
of
Around the
inclination.
axis. Correct. It's always
Yeah.
around the axis. Uh, Okay, and our fixed space coordinate system is actually the world coordinate system. We are measuring in terms of that.
Yeah.
It's interesting though. I mean, you have put the first frame at the origin at the base, while often in lectures, I mean, it's a minor thing though. Often in
It
lectures,
is just
typically 0 and 0 1 are
another
overlapping.
term that you need to multiply and add. It is just another
Yeah,
transformation and nothing more than that.
yeah, yeah, just a minor length adjustment there.
Even if we put or not put, what matters is theta 1 and theta 2 only. So it is very similar to what we did for a 3R planar manipulator. We don't have any third rotation coming in here, right? So your whatever orientation that you're going to get, or whatever position that going to get for x would be, the first link length is L1, L1 cos theta 1 plus L2 cos theta 2, theta 1 plus theta 2. We do not have any third term coming here. For y, it would just be sine of these terms. And here, let's say it is d3, then for z, you will have d3. You can derive all of this from dh parameters. I'm not going into that right away. But all you can do is you can just have them derived directly from here, and since we do not have third r, we won't have that, but we have translation over here, so we get d3 term.
So Soumya, in this case, the first, the frame number 0 to frame number 1, you have not put any length over there. I know it's just a
Yeah.
fixed term there, link length, and the D3 is the prismatic axis.
Right.
And are we interpreting D3 to go down now? That's why we are saying it's minus
Yes, yes,
D3.
yes.
Then should we not be actually some constant minus D3? Because we have not interpreted the frame number 0 and frame number 1 to be coincident. They are apart. Should we not calculate? Should we not account for the delta?
So you're talking about this frame, right? From here to here.
No, 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 no. I'm not talking about that frame. So below R, on your picture, if you see below R, you drew opening
This,
square
this,
bracket. Did you
this.
not? That's correct. So you, and in a way, you are actually going up from frame 0 to frame 1 by certain distance. Let's call
Right,
it L1
right,
or L0, whichever way. And then from L2, you're coming down by D3 because that's your prismatic motion now.
right.
So because your base is at origin 0 is at
Yeah,
x0,
if we
y0,
consider
z0.
this, then we'll have an offset for this as well.
Correct,
That's true.
because we are considering that offset because of the frames right now.
Right. So we should consider this given if we have some like value for this. Let's say if it is capital D, that we have to take this into account. But what right now what mattered was if this is resolved. Okay, and if you write in DH convention, then you'll be only dealing with this, and it would just be an extra transformation matrix. That's it. Okay. So, okay, so till now we have seen everything about direct and inverse kinematics, about joint space and task space, and how direct kinematics are always solvable, they're unique, etc. Uh, After this, should we move directly to the question? Just checking on the slides once. Oh, I think, okay, we did not talk about, in much detail, we did not talk about the inverse kinematics. Uh, okay, so from the slides, uh, if you remember, I mean, I'm not going to prove it, but in inverse kinematics cases, what happens if your degrees of freedom is equal to lambda? Means if you have a spatial robot and it is being operated in the spatial environment, etc. So for special robot, you know that it's already six. If let's say you have a robot with 6 degrees of freedom, this would also be six. So in that case, you get finite solutions when you try to solve for inverse kinematics. Okay, but if n is less than lambda, you have some constraints, and if your degree of freedom is greater than lambda, that means you have redundancy. All right, so what does this mean? Your degree of freedom is more than what is required for that robot. For example, if you are using a robot which can just move in this plane, all you need to have is for or let's take a very particular example. Let's say when we talked about this 3R manipulator, we said that we just have to move in this plane. We are concerned about x, y, and theta. These are enough to define, right? But if you have more number of links, let's say 4, and then you want to move in this xy theta, one of your actuators may get redundant, or maybe if at one joint if you have multiple actuators, then also you go into the case of redundancy. So for example, um, I think I can show one of the robots. uh, I don't know if I'm logged in. I think I'm not logged in here. Uh, just a second. I'll pull up a video. Okay. So if you see this robot, so what is there in this robot? It basically has just 4 motors at 4 of the joints. I don't know if I'll able to mark it. I don't think I'll be able to show it with pen. But anyway, it has 4 motors. So if you see the legs of the robot, it has 4 legs, and at each of these joints we just have 4 motors attached over there. Okay, but then the point is it is able to move have motion in x, y, and z direction, all of them. Apart from that, it is able to maintain its orientation in all the directions. So if it is able to do all of these things with just 4 actuators, it is an example of under actuated system. All right. Under actuated system means you don't have sufficient number of actuators to achieve the desired number of desired degrees of freedom, but you're able to do so. All right. So if you see, it can walk laterally, it can adjust its height, it can move in any direction. And apart from that, it is also able to roll, pitch, and yaw. So in the initial times, we saw that it is able to roll and pitch, etc. So this is one of the robots that we had built in the lab. But yeah, I just wanted to show an example of under actuated system. That's why I came to this. Okay, let's come back to our business. So this was about inverse kinematics, and I'll not go into the details of this planar 3R inverse kinematics. Okay, that can be best understood from the lecture itself. But there, if you have seen, you might have seen, we take a variable x, we take a variable y, define it as x minus L3 cos phi, sorry, and y is y minus L3 sine phi. And from here we try to find out what is cos theta 2, and then we say it is x square plus y square minus L1 square minus L2 square upon 2 L1 L2. I'm not going to details, but what I am coming to is, from here, after writing this, you get plus minus cos inverse of whatever this quantity I have written. All right. From here, you get theta 1 is equal to tan inverse of y x minus tan inverse of, I hope you are aware of what is the difference between a tan 2 and normal tan in the 4 quadrants or in the 2 quadrants. That is it. So L2 S2 L1 plus L2 C2. C2 means cos and L2 means sine. Uh, so your phi would be theta 1 minus theta, phi minus theta 1 minus theta 2 would be theta 3, right? So what I'm saying here is this plus minus, this was important. So this plus minus, when you try to find out theta 2, you'll get it as a form of plus minus. It gives us two configurations. Okay, from here you arrive at two configurations. One is elbow up and second is elbow down. Okay, so this was important. You can look through the derivations. It is pretty simple. You'll be able to understand that. But, and my whole point here was that we can have multiple configurations. If you go for inverse kinematics, you might not move to the same coordinate using the same joint variable configuration. Okay, next thing that I have to cover is workspace. Okay, so if let's say we have a planar robot, then if let's say this is L1 length, this is L2 length. Okay, let's assume L2 is less than L1 for now. So my configuration for this robot in this xy plane would be what? X square plus y square is less than L1 plus L2 ka square, right? We can't go beyond it, right? The maximum radius that can be covered is L1 plus L2 ka square, right? What is the minimum that it can cover? Can anyone answer this?
L1 minus L2 square,
Right,
assuming L1 is greater than L2.
right. So it is L1 minus L2 square. So bigger end effector, if we have a bigger end effector here, then it has less orientation freedom, but that is something different that we'll see later. But as of now, what we care about is this: what is the workspace of your robot? What all space in the environment can this end effector manipulate? That was our business. Okay, so again, for Puma robot also inverse kinematics was done, right? and we saw there that wrist, so there are revolute joints, and then you have wrist where you have the axis coinciding for the last three joints. So the first three joints mainly deal with position. What would be the position of the end effector? And the last three joints basically tell you what would be the orientation of the end effector, right? Also, not going into detail, but you might have seen that there are total 8 inverse kinematic solution for that. And how do we do that? Does anyone remember the trick? What method was used to find this? So one of the methods is elimination, right? You might have seen Sylvester criterion to eliminate the variables, and also optimization and everything. You might have already seen all of them. Here we apply tangent half angle trick. And if you have not gone through it, please go through it once we are done with the lecture, because this is very important. Okay. Apart from this, for Skara robot, uh, so it is all about constraints and everything. If you have, if there is a redundant manipulator, where the number of actuations are more than what is needed, more than the degrees of freedom, then what do you do? So you see, our space has just 6 degrees of freedom. Anything that you do in our space has 6 degrees of freedom. But what if you have more motors attached with more degrees of freedom? In that case, you get infinite inverse kinematic solutions. So how do we deal with this then? We go for optimization. Okay, with, let's say, an objective example is minimize theta 1 square plus theta 2 square plus theta 3 square. Now this optimization can be based on obstacle avoidance. It can be subject to some constraints, and they can be obstacle avoidance. They can be torque minimization, and it can be smooth motion. So you might have heard of minimum jerk trajectory, minimum acceleration trajectory, etc. Okay. Okay, fine. So your workspace defines the reachability, and this redundancy enables the optimization. Okay. So so let's say, let's have a question on workspace first. The link length L1 and L2 for a 2R planar robot are 5 and 5 meters. Okay, with joint restrictions. And what is my joint restriction? Minus pi by 2. Theta I should be in between minus pi by 2 and pi by 2 for I is equal to 1 2, because we have two links. Okay, then the workspace of the planar 2R appears to like what? And I'll give you some options. So if I say my first option is, which is workspace 1, it looks like this. All right, you have Y here and X here. This is your workspace 1. In workspace 2, let's say I have a semicircle like this. Y and X are along the same lines. In third, I have my workspace to be somewhat of this type. Okay, and in fourth, I have my workspace to be somewhat of this type. Okay, So if I ask you that, so this is a classic workspace with joints limits problem, and you should be clear in your concept just to have this. So basically your joint limits, your link length is 5 meter and 5 meter, that is okay. The joint limits lie in between minus pi by 2 and pi by 2. Okay, so your joints cannot move beyond plus pi minus pi by 2 and plus pi by 2. That means both of them should be able to cover some area, and we are concerned about end effector. You should be very clear. Okay, so for a planar to our robot, the end effector position is what? Let's talk about it. So for a planar to our robot, the end effector position is, I hope since we did for 3R, this must be clear. L1 cos theta 1 plus L2 cos theta 1 plus theta 2, right? Y is equal to L1 sine theta 1 plus L2 sine theta 1 plus theta 2. So position depends on two angles, and workspace is definitely a 2D region in the XY plane. That is not a problem. Now, if both the uh, joints were free, okay, that means if both the joints, let's take a case, if let's say minus pi by 2 to pi by 2 was not my problem, then what would have happened? If all the, sorry, if both the joints were free, what does that mean? My theta could have lied in between minus pi to pi. So what would be the maximum reach? It would be L1 plus L2, which is 10. And what would be the minimum reach? It would be L1 minus L2 is equal to 0, right? So the minimum I could reach is myself, the origin, and the maximum I could reach is when both the links do not make any angle with each other and they are in a straight line. Okay, so in this case, the workspace would be full disk of radius 10, right? But this is not our case. Okay, now let's introduce the limits. So my limits are minus pi by 2 theta 1 to pi by 2. Similarly for theta 2, but let's look at theta 1 first. That means joint 1 can rotate only 180 degrees, right? Not more than that. What does that mean? The arm cannot go behind the base, or instead of that, I should write motion is restricted only to right half plane. I think that is very evident. Why? Because your angle limitation is such that you can move only 180 degrees, that too to the right side of it. So workspace cannot be a full circle, and workspace should be a sector right like region, and it should be basically 180 degrees. Okay, but for theta 2 we have minus pi by 2 to pi by 2. Okay, so the elbow cannot fully fold backward. I mean, the arm cannot wrap around it, right? Uh, what should I say? Like, if you have end effector placed over here, okay, then the it should not be that. So we can definitely get complete 0 as well. But for maximum reach, we will have, what are the boundaries that we are going to have? So let's come to this. Let's talk about boundaries first. When theta at 2 is equal to 0 degree, you'll get L1 plus L2 is equal to 10. So the outer boundary is part of a circle but not full, only the allowed angle to sweep in for theta 1, which is minus pi by 2 to pi by 2. Inner boundary, when would it occur? When the angle is theta 2 is plus minus pi by 2, right? जब वो fold होगा पीछे side पे. So in that case, your R minimum would be under root L1 square plus L2 square, and that would be approximately 50, under root 57.07. So the points that are closer than 7.07 meter cannot be reached. This creates a crescent shape hole. Okay, so if I have my, so if I have a full stretch, it is at 0 degree and I can go to the outer workspace, but for inner workspace I cannot completely fold it, because once I start folding it, and if my relative angle with respect to what is fully stretched is pi by 2, then my R min would shrink to this, because I cannot say there also that it is able to go in between minus pi by 2 and pi by 2, because once the link 1 has maintained a certain angle, the next angle is with respect to this link only. So any place that I can reach has to be, if I have to reach here, it has to be a combination of L1 and L2 ka under root, right? So it has to be L1 square plus L2 square. That is the place only that I can reach. I cannot bend it completely and come here, because that would violate, right? I'll have to bend more than pi by 2 to come directly here. The angle which is defined, pi by 2 to minus pi by 2 to pi by 2, is with respect to the first link and not with respect to the walled frame. So your maximum that the minimum that you can reach is under root L1 square plus L2 square. You cannot come beneath it, right? So what happens? This is 7.07. That means points closer than 7.07 meter kind of cannot be reached. Okay. So this creates a crescent shape. Okay. So because theta 1 lied in between minus pi by 2 to pi by 2, so the arm sweeps from downward vertical through positive x direction to upward vertical. This is what theta 1 takes care of. Okay, so this is exactly a 180-degree sweep centered about the x-axis. But then y-axis has also restriction for minus pi by 2 and pi by 2, and hence we need to take into account this distance, that what is the minimum it can go. So outer radius is 10. All right. Outer radius is 10. And the inner radius is 7.07. Okay. But then you cannot have this part. So we will throw away this part. And only this is your answer. So shapes should be C-shaped, but in the opposite direction. So our correct option is this one. Okay, it is a restricted sector. It is not a full ring. It is not a random blob or anything. It is this place. Okay, I hope this is clear. Okay, so whenever we do this such type of question, we should start with unlimited workspace. then apply joint limits one by one. Don't apply all of them together, you won't be able to get the answer. If you apply the limit to joint 2, you won't make sense because joint 1 का अभी बात ही नहीं हुआ है. So first you have to see how much does joint 1 span, then I have to move from there and apply restriction to joint 2, then how much it would expand even more. That is how you proceed. It should be systematic procedure and not saying that if both of them are lying in between minus pi by 2 and pi by 2, that means that I can move in a circle in the right half of the plane and then the complete right half of the plane is my answer. No, it is not, because you have a inner limit, and that arises because when you are trying to like uh, have a limit on the second joint as well, then you have to take care of how much it can move. Okay. You can do this analytically as well, by the way. uh, so this was with certain understanding and intuition. I think I should tell you how do we do analytically, because every time you cannot have intuition coming in, right? So cos theta 1 plus L2 cos theta 1 plus theta 2, y is equal to L1 sine theta 1 plus L2 sine theta 1 plus theta 2. Then let's define the radial distance. Distance of the end effector from the base, and it is r square is equal to x square plus y square. Okay, now what we'll do, we'll compute r square using trigonometric identities. And how we'll do that, we'll just substitute here. Okay, once you substitute and expand it, what we'll get, we'll get L1 square plus L2 square plus 2 L1 L2, right? And then cos theta 1 cos theta 1 plus theta 2 and sine theta 1 sine theta 1 plus theta 2, right? After this, we are supposed to use an identity. If you know, cos A minus B is cos A cos B plus sine A sine B, right? We have to use this for this term. Uh, for this term. Okay. So, once you put everything and then you like simplify it for the right term for what I've put in the red brackets. So it's going to be r square is equal to L1 square plus L2 square to L1 L2 cos theta 2. Okay, you can notice from here where one very important thing is that what is there something surprising once we apply this identity and come here?
There is no theta.
Right, there is
It's
no
purely function of.
yes, correct. So theta 1 is completely eliminated. That means radial reach depends only on theta 2. So what I'll do after this, I will apply. So we radial bound on theta 2, but before that we already know that theta 2 lies in between minus pi by 2 to pi by 2. So my cos theta 2 lies in between 1 and 0. Is that correct? Uh,
Should it be 2 theta in the one? I mean, the above equation that you have, it
huh?
actually simplifies to, in case of this one, it is L1 plus L2 square or L1 minus L2 square. Isn't it? That's how you get the annular disk, the sector, angular sector.
I did not understand what you said.
Sorry, what I said is this equation you have R square equals L1 square plus L2 square plus 2 L1 L2 cos theta 2,
Right.
right? When theta 2 becomes 1, cos of theta 2 becomes 1, this is effectively L1 plus L2 whole square.
Right.
And when cos of theta 2 becomes minus 1, this is L1 minus L2 whole square.
Right.
And that's actually the sector you're talking about, the annular
Right.
sector.
Right.
Isn't it? So in that case, this instead of theta 2, should it be 2 theta 2? Then you get into pi and minus pi. So that depending on the two extents, either you get cos of theta 2 as minus 1 or plus 1. And that's how you get L1 minus L2 and L1 plus L2.
Right. 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 So that is a good way to look at it. So, okay. So again, we have to basically come to the. So what you said is perfectly right. And apart from this, again, we have to come after doing this grinding, we have to come to the same part that R max is L1 plus L2 square, where R max can be max 10, and R min is L1 plus L2 square, and given theta 2 is plus minus pi by 2 at the ends, it is the same thing, under root 25 plus 25 wala case, which is 50 and 0.7.07, that we already did. So basically we come to the conclusion that R has to be in between under root 50 and R. And how it comes, we can take maximum radius. I don't think we need to use it even, so let's remove it. Okay, maximum radius is, when does it occur? When it, as you said, it occurs at cos theta is equal to 1. That means theta 2 is equal to 0. Okay, so R max ka square is L1 plus L2 ka square, or we can directly write this, there's no need to do R max also here, and from here we get R max is equal to 10. For minimum radius, we just have to have cos theta 2 to be equal to 0. That means theta 2 is plus minus pi by 2, and then R min square is equal to L1 square plus L2 square, which is 25 plus 25. So from here, R min is equal to under root 50, which is 7.07. So from here, we come at the following conclusion that it should lie in between this. So it proves that it is ring like the crescent shape and whatever. Okay. And I think this is okay. So basically, what we get is this is the same analytical workspace that we defined analytically. Okay. Okay, let's move to the next question. The next question is about inverse kinematics of the planar 2R robot. With links L1, L2, I think this question I don't need to do because it is already covered in the lecture and you can directly get the answer. So I'm writing a statement. You have to prove it. Not necessarily now, but you should do it. In the inverse kinematics of the planar 2R robot with link lengths L1, L2, rotation angles theta 1 and theta 2, and the end effector position, given by xy, the second angle theta 2 can be obtained by what? What would be the answer to this question? So the answer to this question is plus minus cos inverse x square plus y square under minus L1 square L2 square upon 2 L1 L2. I would request to take a note of this question and please solve it. If you have any confusion, you can come back to this question in the next class. But I think it should not, there shouldn't be confusion because very similar derivation has been done in the lecture. So I'm not doing it right now. We'll move to the next question, but please make a note of it. It's very simple. You just have to start with very basic. X is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2 that we have been already doing. Find out x square plus y square. Substitute the expressions. Again, you are going to have this cos A minus B kind of term coming in. And then you'll have something of sort x square plus y square to what we already achieved. From there, you can find that you can have cos theta 2 to be equal to the same. So essentially, you have to arrive at, where did I write that equation? Yes, this would be replaced by x square plus y square, and I think that is the answer, right? X square plus y square minus L square minus L2 square upon 2 L1 L2 is uska cos inverse is equal to theta 2. So this is what you're going to arrive. So basically the complete derivation is done. Okay, you don't have to do anything, but still I would suggest you to go through it in a very uh, like explore every step and do it and see where are the plus minus sign coming in. Is there some confusion? And you'll get plus minus because there are two configurations, elbow up and elbow down. That is only the reason why you'll have two answers coming in. All right. Okay, so I think so if I give you DH parameter table for Puma robot and the transformation matrix from 0 to 6th link, then I want to find out the inverse kinematics for theta 6. Okay, I want to find out the inverse kinematics for theta 6 in some particular range. How are we going to do? So I'll write a question. We will solve this. For Puma robot, I want the DH table is given by this is I 1 2 3 4 5 6. Okay, this is alpha I minus 1 in degrees. This is a I minus 1. This is a di, both of these are in meters, and this is theta I. Okay, again in degrees. So 0 0 0 theta 1 minus 90 degree 0 0 theta 2 0 0.4318 0.125 theta 3 minus 90 0.019 0. Sorry, this is 432 in the question, theta 4. This is again 90 0 0 theta 5 This is minus 90, 0, 0, theta 6. Okay. So let's say this is a DH parameter table given to you. So for the end effector, orientation and position given in the transformation matrix below, and we have a transformation matrix, okay, well, let's say it is 0.8660 minus 0.50, 0.1855, 0.3536, 0.6124, minus 0.7071, 0.2514, 0.3536, 0.6124, 7071, and 0.1267, and it is 0001. All right. So the question is the inverse kinematics solution for theta 6 we want to find out. In the range of 0 to theta 6 to 45 degrees is what? Okay, this is what we want to find out. Okay, so we have the DH table here, and then we know that theta 1, theta 2, theta 3 basically define the position, and then these basically define the position of the end effector, that how it is placed in the space, and these three basically define the orientation. We are only asked about theta 6. Okay, now my question is, you know very well that this part, this part is a rotation matrix, right? This is a rotation matrix. We will see where it is significant, but this is a rotation matrix that we need to use now. So it is some rotation matrix, and it has a transformation from zeroth to the end effector position. Okay, and then we want to find out what is happening at theta 6. Okay, so my question is, axis of fourth, fifth, and axis 4, 5, and 6 intersect in Puma, right? If you've seen the lecture, you would be familiar with this. 4, 5, and 6 intersect. That means position and orientation are decoupled here. All right. So what we are doing, theta 6 here is not defined with respect to the base frame. That should be very clear to you. We already saw in 3R as well. Theta 6 is not defined with respect to the base frame. It is defined with respect to base 5. So from where does this theta 6 come? I am giving you two options and you have to answer me. Theta 6 comes from the rotation matrix of end effector with respect to the third link, or the third joint, or the second option is theta 6 comes from, okay, from where does it come?
I believe the first one, because of the decoupling nature, the first
Right,
three will give you position.
right. So the first three links that we have actually help me in establishing the position, but theta 6 comes from here and not from here. So the rotation matrix that we have been given here we should take into account how we are going to find this first. Okay, so let's proceed step by step. The most important thing is writing. um, so we want to find this, and this comes by, you know that the properties of rotation matrix, right, that it is R inverse is equal to R transpose and all of that. And that way we can write this, because for end effector with respect to the base frame is basically a multiplication of two rotation matrices. Okay, so if they are decoupled, then we can write key 0 say 3 into third link with respect to base into sixth link with respect to 3, right? We that term would have been here, and then we brought it here by taking the inverse, and it can be written as the transpose. So so after that we need to, so if we, from this dh parameter we need to take in the values. Okay, and when we take it, we'll get, so we know that, just a second, theta r, third link with respect to the third link with respect to the base frame is basically rotation about the z axis with an angle of theta 1, and then x axis with respect to minus 90 degree, and z with respect to theta 2, and z with respect to theta 3. Okay, so this is how we reach to the third link. And when we substitute, theta 1 is equal to 45 degree, I guess theta 2 was 60. This is something that I have taken from the notes directly there. Okay, so theta 2 is equal to 60. So this is being talked about what has been there in the notes. It is not explicitly mentioned here. It is from the lecture example. Okay, so from here, if you try to compute this matrix, you will get a matrix which would have, let's say, you can always verify this, since we are running short on time, I'll not go into the whole calculation, but you'll see that you'll find this to be, this is 0. Once you get this, you just have to compute 6 with respect to 3 is R3 with respect to 0 transpose into 0 with R, and this is already given to you. This was given in the question, and this you have already computed. Okay, if you multiply it, you'll get it also. I am writing the values, please make sure you have note of the values, or moreover I'll be uploading this as well in the uh, on the lecture recording sheet that you already have. So the values that you'll get are, you should verify all of these. Okay, so once you have done this, what you're supposed to do, you have to find out theta 6. Okay, and if you compare it, you will find that theta 6, so you have to compare it to a standard matrix. Okay, and this is important, rz theta 4, ry theta 5, and rotation about z axis by theta 6. So from here you will get theta 6 to be equal to tan inverse of r21 upon r11, because everything is rotation about the z axis, and then you have to just get cosine and sine terms from there, so that you get tan inverse. And if you compute from here, you'll get r21 to be equal to So from here, by comparing to this matrix, you'll get it to be compared to this matrix, and you'll get it R21 is equal to 0.2500. R11 is 0.9336, and from here, if you take the tan inverse, you'll get it to be equal to nearly 18.43 degrees. Okay, so your constraint, which was there, that theta 6 should lie in between 45 degrees and 0 degree, is being satisfied here. So what we actually did, since the system was decoupled, we just went with the last three, the last three axes, okay, which all of them intersected, and they were responsible for the orientation. For that, we tried to calculate this R36, and then we compared it with sine theta, cosine theta, and then we wanted to find out what should be the value of theta 6, and from there we arrive at it. Okay, so it satisfies the constraint also. So the main point was, we do not have to read the end effector frame from base frame directly. This ignores the third frame, and for spherical wrist, theta 4, theta 5, theta 6 live in the wrist frame. Base frame angles are misleading. Okay, this is a very common and serious mistake, so we should not make it. Okay. Okay. I think we can take one more question here, although I have a couple of questions left. But the Sylvester matrix, if you've gone to the lecture, you might have seen Sylvester matrix when we are learning elimination theory and everything. So this question is not about elimination or anything, but this is about how do we construct the Sylvester matrix. Okay, so Px here is sigma I is equal to 0 to 2 ai xi. Okay, and qx is I is equal to 0 to 2 bi xi is given by what is the Sylvester matrix. Okay, this is all we want to know. So can anyone tell me what should be the dimension of the Sylvester matrix that we are trying to obtain?
Should be 4.
Yeah, 4 cross 4. Okay. So how do we do it? So we already have, since we have I going from 0 to 2, let's expand Px and Qx. So Px is sigma of I is equal to 0 to 2 ai xi, which is a naught plus a1x plus a2x square. Similarly, Qx is I is equal to 0 to 2 bi xi b naught plus b1x plus b2x square. Okay, so we are asked to write the Sylvester matrix for this. So what is a Sylvester matrix? It is constructed so that its determinant is 0 only and only if the two polynomials have a common root. You might have seen linear independence condition and everything. So what we want to do basically here is, we want to eliminate x from px is equal to 0 and qx is equal to 0. Okay, so how do we do that? What does this matrix contain? The Sylvester matrix encodes all shifted coefficient equations needed to do that. All right, so from here we see, as of now, that degree of m is degree of p is 2, degree of q is n is equal to 2. So the Sylvester matrix size is m plus n cross m plus n, which is 4 cross 4. First two rows, n is equal to 2 rows come from px, okay, and sorry, next m is equal to 2 rows come from qx. Okay, so this already fixes the number of rows. All right, now so the polynomial, we already have the polynomial, but it always uses a descending power, and writing in this format is not good. This is bad way of writing. It should be written in the opposite direction. So from here we'll get px to be a2x square plus a1x plus a naught, okay, and qx is equal to b2x square plus b1x plus b naught. All right, now we want to construct the rows from px and then qx. So let's start by that. So if we start by px, what it would be? First row, coefficient of px, and then we'll shift, right? We multiply it by x, if you have seen, and then we shift it, if you remember that. So okay, let's do this first. Coefficient of px is a2, a1, a naught, and 0, right? If we shift it, that means we multiply x into px is equal to a2 into x cube plus a1 into x square plus a naught x plus 0, right? So what would happen? It would be shifted. Okay, so after shifting, what we'll get is the following. Okay, so we consider them to be linearly independent. That is different thing. Okay, let's check on the shifting. So second row, coefficients shifted, sorry, right by one position. Okay, so from here what you'll get? 0, a2, a1, a naught. Okay, so these two rows represent, so this row basically represents the first row which you have. It represents x to the power 0 into px, and this represents x to the power 1 into px. All right, similarly for third row, what we'll have? We'll have b2, b1, b0 and 0, and then in the fourth row we'll have 0, b2, b1 and b0. So what do these correspond to? These correspond to, this is x to the power 0 into qx, this is x to the power 1 into qx. So then we need to assemble the Sylvester matrix, and it is basically the following matrix: a2, a1, a naught, 0, 0, a2, a1, a naught, b1, oh sorry, b2, b1, b naught, 0, and this is 0, b2, b1, b naught. So this is the answer to this question. So there is another option. I haven't written down all the options that are there, but there is another option in which it is constructed in the same way, but a naught comes before and a2 comes at a later stage. It is wrong. We have to arrange p and q such that it is in ascending power order. Okay. Oh, sorry, in descending power order. If we have a naught, a1, a2 coming in, then it is ascending power order, and Sylvester matrix is not done in that way. It should be descending power order. Okay, And shifts correspond to multiplying by powers of n. Wrong shifts means you'll get wrong elimination equations. And ai by bi you cannot miss, because rows must come from one polynomial at a time. So in inverse kinematics, trigonometric equations are also derived from tangent half angle substitution, which I already said, and in the lecture it is given in a very systematic way, in a very well taught way. So it leads to polynomial equations. Here we can eliminate one variable and the resultant. The resultant is basically a determinant of Sylvester matrix. So this matrix is not an abstract math; it is a tool for inverse kinematic solvability, right? So so here we just learned how to find out Sylvester matrix. There is a lot of math goes beyond it, and then you try to find out the inverse kinematic solution. But given the interest of time, I won't go into that. But I have a question for you, that if we have RRR manipulator and you want to find out the expression for XYZ with respect to base, I think that you can already do. But it is XYZ. Yes, this you should find out. I'm leaving you with this question today. So for the, please note it down or take a screenshot or whatever you want to do. RRR manipulator, find expressions for x, y, and z with respect to base in the terms of the joint variables and li, where I would vary from 1 to 5. Okay, so what is here is the following. There is a base. Okay, let's say it has a height of L1. Okay, then there is a joint, a revolute joint. So it has an axis of, and rotates by an angle of theta 1 along this axis. Then from here you have another joint, and then you can move from here by tan angle of theta 2, and the link length here is L2. Okay, after this you have, can assignment solution be available in Swayam map? I think after you submit the assignments you get the solution, right? If I'm not wrong. From there you can have. Okay, yeah. So then you have another revolute joint here. I'm sorry, I drew it badly. Yeah, after submission date, right? So after this you can draw it like this, and then this is again your axis of rotation theta 3. Before that, this length is L3. You have, this is L3, and again you have a revolute joint. So basically theta 1, theta 2, theta 3. I did not draw this also properly. So you're rotating about this by an angle of theta 3, and the offset by which this is lying here is L4. So this was important, I had missed this. It is connected here. Okay, but it is using this revolute joint. So the distance between both of them here is L4, and this link length is L5. This is the end effector position, X, Y, and Z. This is the base. Here is the Z axis. Take X, Z0. Which question do you, I'll show just a second. X naught, and in the right hand coordinate frame you'll get Y naught. I don't know if I can zoom this in or out. Just let me change the orientation. No, that would not help. Hold on. What is- Okay. So what you're supposed to do, you are supposed to find expression for xyz, which is the end effector here, with respect to base in terms of joint variables and the link lengths. That is your job. Please write it down completely. Okay. I guess. Bring the call back.
Soumya, I have a question. Maybe once you are done, I can ask.
Yes. Just I'm about to complete. Um, just before that, Manas, you had a question in the beginning. It was something about hook joint, right? Hello, Manas is not here. Okay. Okay, so yeah, you can go ahead with your question since he is not here.
Okay, thank you. So you're talking earlier. I'm just trying to gain some insight from you. Earlier in the session, you were talking about redundant manipulators. You very briefly spoke about them, and then you said that at certain point of time, you can specify the optimization criteria, and one of
Correct.
the optimization criteria could be theta 1 square plus theta 2 square plus theta 3 square.